It is a moment of profound domestic convenience, a simple flush barely registered in the daily rhythm of millions. Yet what appears to be an instantaneous disappearance is, in fact, a massive hydrological event.
In a megacity like New York or Tokyo, that single act contributes to a torrent of water volume and velocity entering the subterranean arteries beneath our feet.
We often think of this flow as mere waste, but the sheer scale is staggering. Consider the cumulative output. Billions of gallons passing through these hidden networks every day.
This isn't just sewage. It is an immense, powerful resource stream, a complex mixture of water, energy, and material that demands sophisticated management.
Understanding what happens next means understanding the physics and chemistry of this constant, colossal flow. This subterranean river carries everything: dissolved chemicals, organic matter, and even microplastics. The
journey continues deep beneath the city's skin. Here, gravity is not merely a force. It is the primary engine.
Vast networks of pipes, some laid decades apart, work in concert to move this colossal flow toward treatment centers. The sheer scale of this infrastructure is staggering.
We encounter different engineering solutions: combined sewer systems which handle both stormwater and wastewater, and separate sanitary lines. Each presents unique mechanical challenges.
Engineers must map these arteries, a labyrinth beneath concrete and subway tracks, to ensure continuous, reliable movement.
This initial collection phase demands robust design to manage immense volumes of varied waste, a constant challenge of physics meeting urban density. The gradient must be precise. Even minor dips can cause blockages.
These subterranean rivers of waste flow through materials ranging from cast iron to modern PVC, a testament to continuous civic engineering under immense pressure.
The raw municipal flow, having navigated the city's arteries, now arrives at its first major checkpoint, the headworks.
This is where the process of preliminary screening begins, a mechanical interception designed to remove anything too large or structurally disruptive for the subsequent stages.
Massive screens act like industrial sieves, catching everything from discarded plastics and textiles to construction debris. Following this initial physical barrier, the flow enters grit chambers.
Here, the water slows dramatically, allowing heavier inorganic materials, sand, gravel, and small stones, to settle out by gravity.
This two-step mechanical filtration is crucial. It doesn't treat contaminants chemically, but rather polishes the raw stream by removing the bulk solids that could damage pumps or clog finer equipment downstream.
It prepares the water for a deeper, more complex purification journey ahead. The resulting slurry, now significantly cleaner, moves onward. This initial grit removal.
The refined slurry, having passed through mechanical filtration, is now ready for its biological transformation. Here, nature takes over. Massive bioreactors become thriving ecosystems, populated by specialized microbial life.
These invisible organisms are the true engines of purification. They consume organic pollutants, the nitrogen and phosphorus that make up much of our waste stream, through natural metabolic processes.
In what is known as activated sludge, these microbes literally eat the contaminants, converting complex chemical compounds into simpler, less harmful byproducts like methane gas or harmless nitrates.
Simultaneously, anaerobic digestion occurs in sealed tanks, where oxygen deprivation forces different microbial communities to break down even more stubborn organic matter.
This entire process isn't just filtering. It is a massive, continuous biochemical conversion that fundamentally changes the nature of the wastewater itself. The resulting sludge, now stabilized and nutrient-rich, represents a valuable resource.
But stabilization is only half the story. To truly prepare this water for any subsequent use, whether it's irrigation or industrial cooling, it must undergo advanced purification.
Here we move into tertiary treatment, where the focus shifts from bulk removal to microscopic refinement. Techniques like deep bed sand filtration and modern membrane bioreactors are employed.
These systems act as highly sophisticated barriers, trapping remaining suspended solids, fine particles, and even pathogens that slip through earlier stages. The process is a meticulous physical and biological polish.
By utilizing semi-permeable membranes or complex filter media, the effluent achieves an unprecedented level of clarity and purity.
This final polishing stage is what allows megacities to responsibly reclaim their water, transforming what was once waste into a viable resource. The resulting water quality often meets stringent WHO guidelines.
This advanced purification ensures that recycled effluent is safe.
The journey does not end at the treatment plant's outflow gate. Instead, it enters a sophisticated network of secondary uses, closing what engineers call the urban water loop.
This highly purified resource is far from being simply dumped back into the river. Its value dictates multiple destinations.
It can provide cooling water for industrial complexes, reducing the strain on fresh sources.
It can irrigate vast agricultural fields in arid zones, sustaining food production without depleting potable reserves.
And critically, after rigorous safety checks and advanced treatment protocols, including reverse osmosis and UV disinfection, it can even be reintroduced into the drinking supply itself.
This concept of circularity is fundamental to future urban planning, moving from a linear take-use waste model to a resilient closed-loop water economy. This systemic shift ensures urban resilience against drought and contamination.
By treating wastewater as a valuable asset, not.
But the journey doesn't end with purified water. Even after advanced treatment, there remains a solid byproduct, the concentrated sludge. This material represents both an environmental challenge and a potential resource.
To manage it effectively, modern facilities employ sophisticated processes like anaerobic digestion. In these sealed bioreactors, microorganisms break down the organic matter in the absence of oxygen.
This process is critical because it captures methane gas, or biogas, which can then be scrubbed and used as a renewable energy source for the plant itself.
Furthermore, the remaining solids, known as biosolids, are stabilized.
When handled correctly, these nutrient-rich materials can be repurposed, not as mere waste, but as valuable soil amendments or fertilizers for agriculture, completing the circle of life from tap to field.
These stabilized biosolids are then tested rigorously for pathogens and heavy metals before being safely distributed.
But the circularity is constantly challenged by forces far beyond human design. The infrastructure designed for yesterday's climate struggles against tomorrow's extremes.
Extreme weather events, be it flash flooding or prolonged drought, can overwhelm the very systems meant to manage them, creating bottlenecks and failures at critical points.
Population growth only compounds this stress, demanding more capacity from aging pipes and treatment plants that were never intended for modern megacity density.
The engineering challenge is immense. How do we modernize sprawling, subterranean networks built over a century, while simultaneously adapting them to unpredictable climate pressures?
It requires not just better technology, but a radical rethinking of urban resilience itself. Engineers must now integrate nature-based solutions, like permeable paving and green roofs, with traditional gray infrastructure.
This dual approach is vital for absorbing excess water and ensuring that megacities can truly withstand the escalating pressures of a changing planet.
But to focus solely on the wastewater stream is to miss the larger, more profound picture.
What we are witnessing is not merely plumbing. It is an immense, invisible utility, a circulatory system for civilization itself.
From the power grids that run beneath our streets to the massive subterranean pipes carrying away waste and delivering clean resources, modern life depends on a breathtaking web of interconnected networks.
These systems, often unseen, function as the fundamental pillars supporting human density. They are triumphs of engineering, yes, but they are also fragile commitments.
Maintaining this complexity, from treating billions of gallons of water to powering the lights that guide our lives, demands not just continuous investment, but a radical new form of stewardship.
The future of the megacity rests on keeping these vital lifelines flowing, adapting them for centuries to come.